All right, today we're going to start chapter 12. We're going to take a look specifically today at vector valued functions. And just like when we define a lot of other things, much of what we do is going to seem like, I know how to do this already. You're just doing it on new objects, specifically vector valued functions. So first, a definition of what we're talking about. A vector valued function R of t, okay, so it's a vector function, equals f of t I plus g of t j plus h of t k, where f, g, and h are real valued functions of the parameter t. Okay, so far all we've done in terms of vectors have been straight vectors. I mean, like, just from the origin straight out to our point is how we've really thought about them. It's not what we're doing anymore. We're looking at vectors that are defined by functions for each of the different components that we're looking at. And we're going to do the things that we've done with other functions all the way along through algebra and calculus. We're going to talk about what it means to evaluate a function at that point. What does it mean to talk about the domain of the function at that point? And also today we're going to look at what's going to mean to talk about the limit at that point. Okay? So we're going to start with domain. So we're going to find the domain of the vector valued function and the one we're looking at is R of t equals the square root of 4 minus t squared I plus t squared j minus 6t k. So there's three components. There's three different equation components, right? Polynomials or radicals or whatever, but there's three different f, g, and h. There's three of them. Two of them you know the domain for at a glance, real quick. Which two do you know the domain for real quick?
T squared and negative 6t.
Yeah, t squared and negative 6t. What's the domain for t squared and negative 6t?
All real.
All reals. Yeah, there's no problems with domain there. So just to show that we've sort of thought through it, this one's all reals. Negative 6t is also all reals. The other one, 4 minus t squared underneath the radical, does not have that feature to be true. So what is the potential problem with a radical function when real numbers? Yeah, if the value underneath it is negative, right? So in particular, what we want is we want 4 minus t squared to be positive. Now, it's probably been a minute since you've solved inequalities like this. It's a college algebra topic, but it's probably been a minute. So what we do is we factor it. So this would be 2 minus t and 2 plus t. That gives us, these are critical points. We're actually finding where those are equal to 0. So this happens to be then at 2 and negative 2. And we create a sign chart. So my sign chart includes the numbers 2 and negative 2 on it, in correct order, of course. And I need test points in between. So I'll test values that are on either side of these and in between these values. So maybe you test negative 3 here, and you test maybe 0 in the middle. That's kind of nice. And you test the number 3 on the right. You have a couple places where you can put those values in. You can put them into the actual 4 minus t squared and decide, am I getting a positive or negative? Or you can actually think through it in terms of the signs of the individual factored pieces. Either way will give you the correct answer. If you put in negative 3 Do you get a positive or do you get a negative? What do you get? Negative, yeah. What if you put in the 0?
Positive.
Positive. And if you put in a 3? Negative. So which one of these are the ones we want to have?
-2 to 2.
Yeah, this interval right here from -2 to 2. So my range is actually from -2 to 2, and it's including the interval endpoints. I can take a square root of 0, so that's not a problem. So my domain is -2 to 2. But I need a domain that's good for all 3 components. Now, in this case, the only component that had any problems was that one, right? So there's really nothing else I have to do. But let's say, for instance, that I had one of them, like I have right here, that's -2 to 2, and the other one was only positives. Well, then I have to consider where they overlap and give the most restrictive values that will work for everything. So for this one, I don't have that issue. This one, the domain really is just -2 to 2. But in general, I could have something where I had overlapping regions to consider. Does that make sense? You okay?
Yeah.
Okay. All right. Evaluation, I mentioned this one is 4-2. Evaluating a particular vector. So if we take a look at these directions, so we're going to evaluate. I should start saying example first, sorry. Example number 2, evaluate the vector valued function. And the one we're going to look at is r of t. We're going to do just 2 vectors. So it's going to be cosine t I plus 2 sine tj. And we're going to evaluate this at 0. And then we're going to evaluate it at pi/4. All right, so if I evaluate at 0, it's going to work just like it did when you were evaluating functions that weren't vectors, right? You're just going to be putting 0 in for all of the t's, because t is my variable. So I will have cosine of 0, I, plus 2 sine of 0, j. That's what I'm doing. What's the cosine of 0?
1.
1. And what's the sine of 0? 0. So what does this vector become? It's just I. Right? How about pi/4, excuse me. So now I've got cosine of pi/4, I, plus 2 sine of pi/4, j. So what's the cosine of pi/4? Square root 2 over 2. And what's the sine of pi/4?
Square 2 over 2.
So I have the 2 sine, so it's 2 times square root 2 over 2 for j. And if we simplify just a touch, we will end up getting the 2's here to cancel, of course. So I have square root 2 over 2 I plus the square root, let me move this over just a little bit. Square root of 2j. Straightforward enough? Yeah, like everything you expect or think should work is working, right? We haven't encountered anything that seems like, oh, well, that was unique or interesting. It's really not. It's very straightforward. We got a few more. This one's the most interesting for sure that we've seen. Are you ready for it? We're going to draw a fun graph even. You'll be able to draw it, I believe. We'll try. Okay, so this is number 3. We're going to sketch the curve represented by the vector valued function and give the orientation of the curve. Orientation is talking about clockwise, counterclockwise. That's what we're looking at. How's the curve going directionally? And this is our function. So r of t, excuse me, equals 2 cosine of t I plus sine of t j plus 3t k. And then we're actually told, or actually we can identify then what's happening in the 3 directions. So we're drawing this in an ordered Cartesian plane. Draw it right, like this. So we have our x direction, our y direction, and our z direction. And each of these components, I, j, and k, correspond, of course, to the x, y, and the z directions of the axes. So our x is actually the 2 cosine of t, and our y is the sine of t, and our z is 3t. Now, thinking about parametric equations, because that's what these are, right? These are set up in terms of the parameter t. What could I do to create an equation for the moment that ignores the z? I just want to create the equation that combines the x and the y together in a very nice way. Let's do this. Let me ask a different question. Ignoring the z again for the moment, let's just draw a 2-dimensional graph of what's happening with x and y. I think that might be good enough help. All right, so if I draw a graph, we're just going to do a number line to talk about what they are for t, and then x and y. We're dealing with trig functions, right? So it would be helpful to use values that would be unit circle type of values. So let's just do like 0. I think actually 0, pi halves, and pi are probably enough. If not, we'll continue. If I put in 0 into this, what is the cosine? 2 cosine of 0. It's 2. How about for y? What's sine of 0? It's 0. How about pi halves? What is 2 cosine of pi halves? It's 0. What's sine of pi halves? 1. So let me actually plot those two first, and then we'll plot our third one as we go. If I'm drawing this as such, I've currently got the ordered pair 2, 0, and then 0, 1. How about at pi? What's 2 cosine of pi? Negative 2. And what's the sine of pi? 0. Can you tell what picture I'm drawing? Really close. An ellipse. Yeah, this one's an ellipse. I would expect that it would have the same value down here at the bottom. That was not a great ellipse, but we'll go with it anyway, more or less. I have an ellipse. If I'm sort of looking down from above, if you will, on the z-axis, so that the z-axis is not doing anything to it, right? The graph itself of the x and the y coordinates are just going around in an elliptical pattern, right? Like the solar system stuff, right? It's just going to keep going round and round and round. But the z value is not. What is the z value doing over time? It's 3t. So what is the z value doing? Increasing. How? At what kind of a rate? A rate of 3, specifically a constant rate, right? So it's going around in this elliptical pattern and constantly going upward. What shape am I getting when I do that? A spiral is what it looks like, or a spring. That's what it actually ends up looking like. So if I were drawing this 3-dimensionally, we can be a little bit careful. We know it's going to start over here at 2 and go through at 1. But it's going to be doing, actually that's not quite true. It's going to be going through 2 and 0 here. But then I'm actually going to be going spiraling around, like you guys mentioned. But I'm increasing my height as I do it. the graph's doing something like this. There's actually a name for this. So does anybody know what the name for this might be? Have you seen something like this before in maybe a science class somewhere? Let me write down our description of what we said it was doing. It's an ellipse, and it's spiraling up, right? So this is actually called, this isn't something I'm going to quiz you on or anything, but you should know what it's called. It's an elliptic. That makes sense, right? It's an elliptic helix. Have you heard the word helix before? In reference to what? DNA. And can you see that picture now that you're looking at it, how it's doing that? Yeah. So let's talk about orientation. I didn't do that part of it yet. When I was drawing my two-dimensional picture, that's probably the most helpful for determining orientation. What is the orientation of this guy going? Yeah, it's counterclockwise, right? It was moving in this direction. So my orientation is counterclockwise. The equation that I was trying to sort of prompt you into of how to relate these, I'll just mention it here because it might be helpful as you're working through other things later. When I'm dealing with sine and cosine, we have a Pythagorean identity that's a really nice relationship for them. And I know you guys know it, that the sine squared of t plus the cosine squared of t is equal to 1. Right? X and y are sines and cosines here. Agreed? At least some variation of it. So like the x value is actually 2 cosine. So instead of writing it as 2 cosine, because I've only got cosine, I can actually write this then as x over 2. So the cosine value itself is half of an x. And then the sine value is actually equal to the y. And you can see that ellipse popping out as you do this, right? We have y squared plus x squared over 4 equals 1. And that's the ellipse pattern that we had seen it in earlier lessons. So that's another perspective of how to think about what kind of equation is this creating. So collapsing one of the variables is nice. Taking a look at relationships between the vector valued components that it has is also another way to do that. Any questions on that one? Okay. Knowing the name of it is not the point. I just wanted to make sure you knew it because it does have a name. Most of them don't, of course. All right, we're going to look at another one. We're going to represent, this is number 4. Represent the curve by a vector valued function. The curve that we have that we're working with here is x squared plus y squared plus z squared equals 4. And how much of this is given before it? Yeah, the rest of this goes to. Let me keep going, sorry. X plus z equals 2 with x equals 1 plus sine of t. All of this is the given information to start with. All right, so what we're doing is we're going to attempt to take each of the pieces and we're going to create a parameter that we're using for the pieces of the vector valued function instead of representing it all as one equation. That's our goal. This kind of has the feel to it of decomposition back in college algebra, where you have this composite function, you're trying to decompose it. And the purpose of learning decomposition is partly in helping you to be able to move on later and look at chain rule problems inside and outside functions, actually. And so this has the same sort of thing. It is not helpful. This one is actually very nice because they give you the parameter. They tell you x is equal to 1 plus sine t. So they give you a parameter relationship to start with. They don't always do that. And if they don't do that, you get to have some freedom to pick. And there's lots of things you could pick. What you can't pick is simply something like x equal to t. Because it doesn't change anything, right? You're just swapping out variables. You're not really assigning a parameter change to what's going on. So keep in mind, you're trying to find something that will work nicely. This one was given to us, so we're going to use this to start with. So they tell us that the x is equal to 1 sine of t. And so we can actually use that information and the second equation that was given, that x plus z is equal to 2, to figure out z pretty quickly, right? So that's where we're headed next. So my z value, if I move x to the other side, is 2 minus x, and the x value they gave me was 1 plus sine t. So what will z be? 1 minus the sine of t. And then what would I do to find y? Yeah, Caleb's saying it and Hannah's like motioning for it. Yeah, you guys are both right. You're going to use that x value and that z value that are now in terms of t in the equation that's got all the squareds in it, right? So now we have x squared. So x is 1 plus sine t squared. And then plus y squared, which is the one we don't know, plus my z squared, which is 1 minus the sine of t squared. And it's supposed to equal 4. So we're going to do some algebra, right? We're going to square some things out, and we're going to see what things we can combine for combining like terms. I have 1 plus 2 sine t plus the sine squared of t, and I have my y squared. And then I have another 1, and I have minus 2 sine of t plus the sine squared of t equals 4. Okay, so some of these things clean up nicely. Some of them cancel out completely. What do you see that you can do? Cancel the 2 sine t and the negative 2 sine t. What can we combine? That's the only thing that cancels, so. Yep, so I've got a 1, and I've got a 4 on the other side. So if we wish, we could actually move the 1 and the 1, which is 2, over to the 4, and this will become a 2. So I've taken care of all my constants. What else? I'll mark them, and I've taken care of them. Yeah, there's a couple of them, right? So I've got 2 sine squared of t, and I have my y squared. So that's pretty good considering all the things that were messed to start with, that it's condensed down that far, right? But the goal is to solve for y. So I need to move the sine squared, right? And I need to take a square root. So y is equal to the square root of 2 minus 2 sine squared of t. There is a nicer way to write 2 minus 2 sine squared of t. Do you notice anything you could do? Okay, I can factor out a 2.
1 minus sine squared is
You got it. 1 minus sine squared is cosine squared. So this is square root of 2, and then cosine squared of t. And if I square root that, then I will have a nicer, more condensed form of this. Hang on. That's not working for me. Okay, that'll work. So this is actually the square root of 2 and then cosine of t. So my vector valued function, I'll write it with the ijk since we've been doing that mostly this section, is that r of t is the x value, which was 1 plus sine t I, plus the cosine value that I just got for y, so square root 2, and then cosine of t j. And then the last one was the k, or the z value next to k. So I have 1 minus sine of t. Okay. Okay, is that all right? Yeah, Hannah.
Do we ever have to pick parameters for ourselves or no?
There are ones that you do have to pick the parameter for yourself. What that means is that you have flexibility. So for example, looking at this, if you had seen some of these things at the beginning, you might have made a decision that said something like, that x is equal to the square root of t. That might have been a really nice one to use here. Can you see how that would be helpful? Yeah. So there's things that are usually kind of, looking at it, you're kind of like, oh, that looks like it would be a nice choice. The algebra afterwards would work out nicely. But the reality of the situation is that you have freedom, which means that you could choose something, Hannah, that's completely different than what Annika does, and you can both be right. And so grading makes it very difficult. My guess is that inside of WebAssign, they're probably going to give it to you because they don't have the ability to grade, a free response kind of thing like that. It's just not possible. Yeah.
Especially when they have trouble graphing things.
There's all sorts of funny things with technology, aren't there? Yeah, for sure.
Just wait till they can graph random surfaces.
Yeah. Okay. Limits. You already look at limits? Okay, limits really, just like before, are just like what you would expect, okay? So let's take a look at what limits are. This is a throwback to Calc 1 right here. So a couple definitions as we move into these, and then we have two more examples, I think, at the end, maybe three. Two. So if R of t is as we have been defining it, it's f of t I plus g of t j plus h of t k. Then the limit as t goes to a of r of t, I'm going to move that down to the next line. You don't need to erase anything, but it's just going to run a space, equals the limit as t goes to a of f of t I plus the limit as t goes to a of g of t j plus the limit as t goes to a of h of t k. Right, the limit of the whole thing should be the limit of the three separate functions. That's it. Again, exactly as you would expect. And all of this has to be, however, provided the limits exist. And you might remember that when you talk about limits, part of the purpose in doing so is to talk about continuity of what you're working with. And so the continuity definition follows naturally from this. So R is continuous at t equal a when, and there's three features that have to happen, even back from Calc 1 for these things to happen. The first one is that the limit has to exist. So the limit of t of a of r of t exists. The second thing is that the function value exists. And the third item is that the limit actually equals the function value. And that does not have to be a given piece of information. You might think about like graphs where we had holes in the graph and then you defined the point to be somewhere else. So things like this should pop into your mind from an algebra standpoint, perhaps. Right? The function value exists, it's the closed-in dot. The limit exists, it's the open dot, but the open dot and closed dot are not the same spot. So this is what we can't have happen for something to be continuous. All good? So we're going to find the limit, and we're also going to determine places where something's continuous. Two separate examples. First, whoa. All right, there we're going to find the limit if it exists. And this one's actually given to us in our bracketing notation. The limit as t goes to 0 of sine of t over t cosine of t and t plus 1 over t minus 1. Okay, so when you do algebraic limits in Calc 1, what you're attempting to do the majority of the time is find some way that you can just put the number in for the variable, right? That's what you're trying to do. You're trying to say, okay, I just want to take t equal to 0 and make t equal to 0, right? And if I can, then I'm good to go and I'm done, because if I can't, then I have more work to do, more work to think about, I have to figure out what's going on. In two of the cases, I can do that on this particular vector valued function. Which two are good to go with just being able to put it in? Yeah, y and z, the last two, right? So what is the, we'll leave a space for the first one. What is the value for the second one, for cosine of 0? 1. And how about for 0 plus 1 over 0 minus 1? You'd have negative 1. Okay, so in these two cases, it is totally appropriate and it makes sense to do this. In the first one, it doesn't work. I can't just put 0 in because I end up getting sine of 0 on top, which is 0, and I get 0 on bottom, which is 0, and I have an indeterminate form, 0 over 0. And when I have 0 over 0, anything can happen. So L'Hopital's rule is one of the things that you've encountered along the way. It is not the best reason for why this actually works, but it does give you the right value, so that's fine. If I were to use L'Hopital's rule here, what would I get for, I'll just jot it down, sine of t over t. So if I applied L'Hopital's rule here, what would I turn this into? It's not equal to it, but what would I turn it into as far as limits are concerned? Cosine of t over 1. And if I did that and I evaluated it at t equal to 0, what would I get? Yeah, I'd get 1, right? Somewhere along the way in, well, actually in Calc 1, we defined this one, and you may or may not remember doing so. I remember it, but that's because I've taught it recently, in all fairness. So the limit as t goes to any value of, hang on, not any value, it's t equals 0 specifically. I was just thinking, like, that doesn't sound quite right. Of the sine of t over t. By definition in Calc 1, this is equal to 1. There's a definition for that to be happening. And then somewhere along the way, a little bit further, we talk about something called the squeeze theorem. Do you remember that? The squeeze theorem actually says that if I were to have taken values that surround sine, namely sine's trapped between -1 and 1, right? And if I were to divide all those by t, and t is positive, that starts to look a lot like what I want in the middle. And I could put limits in all those three places. And if I have the limit of -1 over t as t goes to 0, I have the limit in the middle here. And I have the limit over here. The things we did with sequences and series, those are very familiar things to you, right? What happens if we're taking a look at letting the denominator go to 0 of -1 over 0? Hang on, what did I do wrong? I take a step back. This isn't the right one. This is a different one. I take a step back. It is the squeeze theorem. It's not done this way. We're going to push pause on that. I'll let you talk about it later. It is sine of t over t is equal to 1, but not from that perspective. That's another theorem that I was thinking of. My bad. Okay, we have, what was it, up here? So we'll just talk about the fact that we applied L'Hopital's rule here. And you guys got a 1, so we have this over here. 1, 1, and negative 1. Okay, all good, aside from my faux pas? Thanks. Okay, last one. I think I have enough space. We'll try. If not, I'll shrink some things. So this is example number 6. We're going to determine, this kind of goes back to the very beginning problem that we did. We're going to determine the intervals on which R of t is continuous. And the R of t that we're going to look at is a little more interesting than many of them we had seen earlier. We have cosine of 5t, and we have tangent of t, and we have the natural log of t. And all of these are functions that you are familiar with. This is similar to the domain question from the very beginning. You know, we think about it in much the same way. We identify for each of the functions where they are continuous, and then we have to look at the overlapping regions. So we're going to start with the easy one. The easy one's the first one, cosine of 5t. Where is cosine of 5t continuous?
All readings.
Yeah, everywhere, right? It's those sinusoidal curves that just keep going wave pattern. They don't have any problems with continuity. So for the first one, so we'll put this one as cosine of 5t. It's continuous on all of the real numbers. Indeed. How about the next one? Do you remember what happens with the tangent graph? Yep. We have a lot of repeating images. They look like this, right? The individual pieces themselves are continuous, but in between them are asymptotes, yeah? And there's infinitely many, but they occur at regular intervals. So my problems with continuity are exactly on this one, my problems with domain, which is why this question feels so similar to the first one that we looked at, though we didn't do it for tangent. Do you remember where tangent has any of those asymptotes?
So is that at pi over 2 or 3 pi over 2 or anything pi over 2 plus pi?
Okay, so I'm going to take exactly what you said, and we're going to write that down. So it starts out with the pi over 2. So this is not continuous. Well, let me actually write it this way. It's continuous for all. Oops. For all t such that t does not equal pi over 2. And then what did you say, Jubal, after that? How do we... 3 pi over 2, and then 5 pi over 2. How far apart are each of them? That's what you're going. Plus k pi. So k pi or n pi, whatever you prefer to use. K is an integer for this to work. That's the integer notation. I hope that's familiar to you. If not, we can talk later about those. But k is an integer. Whoa. Wasn't what I meant to do. Okay, there we go. So that's tangent. The next one's not as bad. What about natural log? It's not continuous everywhere, but where is it continuous?
Greater than 0.
Yeah, so it's continuous for all t that are greater than 0. So we need the overlap of these three quite different, intervals to talk about where it's continuous. Where is our graph continuous? So we combine them all together, and we combine them all together in the best way that we can, and sometimes we're able to combine them better than others. This one's a bit messy. So it's going to be continuous for all positive t, so for all t greater than 0, such that t does not equal those same pi over 2 multiple values that we just saw. So pi over 2 plus k pi, where k is an integer. I don't know why I put a bracket there, don't either. Okay? And that's exactly what we would have done with domain if we had had the opportunity to have 3 different functions that might have overlapping or non-overlapping intervals of things we could use. Okay, I'm going to write down the homework. There's one that I messed up on when I was writing it. I wanted to look at the printout real quick to make sure I had grabbed the right number. I did. Okay. All right, so the homework for this section, due Monday. Whoops. We are on page 825, numbers 5, 6, 11A, B, just that 2 parts there, 24, 32, 33, 55, 58, 66, 69, 72, and 75.